This is the video for problem number 1 of review test number 4, where we're working on the shear and moment diagrams and figuring out the shear and moment as a function of x between two places, before and after the 600-pound force. So the first thing we need to do is draw a free body diagram because we need to know the reaction forces. So just by inspection, I'm still going to write it, but the sum of the forces in the x direction equals 0. So we know that A of x equals 0. And then I'm going to take the moment about point A. You could do the moment about point B. It would still give you the answer you're looking for one of the supports. So I'm going to take the moments about A equals 0. And I'm going to have that 600-pound force. Oops, my bad. It is negative, and I forgot to put a sign on it. It is negative 600 times 5 feet. And then B of y is going to be positive times 12 feet, which gives us that B of y equals 250 pounds upwards. Now I'm going to find A of y by summing the forces in the y direction. And I'm going to have A of y minus 600 plus 250 equals 0. So I'm going to get that A of y equals 350 pounds, also upward. So the next thing I need to do, so I found that for our shear and moment diagrams, we need to know that. The next thing I need to do is determine our equations for the internal forces from 0 to 5 and from 5 to 7. So the first thing I'm going to do is draw the free body diagram from 0 to 5. So I have got a reaction force where A is, and I calculated that to be 350 pounds. And then in that 0 to 5, that's all I have. The only other thing I'm looking for is I'm going to have the shear force. I'm going to have the normal force, which is 0, but I'll still draw it just to make it so you're used to seeing it. And then I've got the bending moment, which is going to be counterclockwise is positive when I cut the beam at the left. And I'm going to define x as my distance from A on the beam. So that's what my x is. And then I'm going to define that as O. I'm going to sum the forces in the y direction first, because that's the easiest thing to do. And in the y direction, I only have the 350 pounds and the negative v. So from 0 to 5, v is going to equal 350. Now I need to look at the moments, so let's sum the moment about point O. And so I'm going to have from point O, I'm going to have that positive moment. It's the bending moment there, the internal force. And then I'm going to have the negative reaction from A at 350, and it is x away equals 0. So if I solve that for m, I get that m equals 350 times x. So that is my function from 0 to 5. Now let's look at our internal forces from 5 to 7. So let's see what reactions we have. We still have the reaction at A of 350 pounds. But now we're going to include that 600-pound force, because we're going further than 5 feet. And then the only other forces I'm going to have are the internal forces, since I cut the beam. So I'm going to have the shear, the normal, and the counterclockwise bending moment. And I'm going to say that point at the end is point O for when I sum my moments. And my distances from A to the 600-pound force is 5 feet. and I am still going to call the distance to O from A as x. So now if I sum my forces in the y direction, I am going to have that 350-pound force up. I'm going to have that 600-pound force down. And I'm going to have the shear going down equals 0. So I'm going to actually get that V equals negative 250 from 5 to 7. Excuse me. And so at that point, let's sum the moments about 0.0. So we can figure out what our bending moment is. We have a positive bending moment plus the 600, and its distance away from O is x minus 5. And then I'm going to have the 350 pound, which is a negative 350 pounds times x. Its distance is just x equals 0. So when I solve that for m, I'm going to get that m equals 3,000 minus 250 times x. So those are my functions. So if I was asked to solve for my functions, those are my functions. I've got v and m as a function of x. V is not dependent on x, just changes at the 5-foot mark. So now I'm going to draw my diagram. So for my diagram, I've got my axes here. I need to put in what my reaction forces are. I've got 350 pounds there and 250 pounds here. So when I look at that for my first table, which is my shear, which is in pounds, I'm going to start at 0, and at 0, I already have a 350-pound force going up. So let's say that is 350. And then it continues until I get to 5 feet, which I have marked. And then it's going to go down to negative 250. It's going to be around here. That's negative 250. And it is going to stay there. So we're going to go down here where we go minus 600, because 350 minus 600 gives 250. And then we're going to go back up because we got the 250 up at the end to 0. So that is my shear diagram. Remember, we shade in from the axis. I'm going to label my points. This is at 5 feet, and this is at 12 feet. And this axis is x in meters. So now let's look at our moment diagram. So remember, our moment diagram is going to be related to our shear diagram. So our moment diagram, we are in feet pounds. And we are going to start at 0. And at 0, our moment equals 0. When we get to 5 feet, how do we calculate what our moment is at 5 feet? We use our equations. So let's use we should be able to use either equation. We can double check. So at x equals 5 feet, from the left, m equals 350 times 5, which equals, oh no, I lost my calculator. And from the right, m equals 3,000 minus 250 times 5, And from either of those, I'm going to grab my calculator, but I don't have it right now. I'm going to get 1750. So that is where my peak is at 5 feet, is 1750. And you can see it's a positive above the axis for 0 to 5. So I'm going to be going in a positive direction for my moment from 0 to 5. And then I'm going to be going in a negative direction because my information is below the axis for this year. So that's going to be my moment diagram. And that is it. So that is the answer. All right, on to our next problem.